Welcome to part 5 of our Java Collections Mastery Series. Today we are exploring Deque implementations, double-ended queues that enable operations at both ends. We'll cover ArrayDeque, LinkedBlockingDeque, and ConcurrentLinkedDeque. That makes modern concurrent system so efficient. Understanding these Deque implementations is crucial for building high-performance systems, whether single-threaded or massively concurrent. Let's begin by understanding what makes Deque so special. A Deque, pronounced Deque, is a double-ended queue that supports element insertion and removal at both ends. Think of it as a line that allows people to join or leave from either the front or the back. This dual end capability enables powerful patterns that regular queues can't support. Unlike regular queue, which is first in first out, or stack, which is last in first out, a Deque can behave as either depending on which end you use for operations. Let's explore the simplest and fastest Deque implementation. ArrayDeque. ArrayDeque is a resizable array implementation of Deque interface designed for maximum performance in single-threaded scenarios. It's the go-to choice when you need Deque operations without thread safety requirements. Java's own documentation recommends using ArrayDeque instead of the legacy stack class when you need stack behavior, and it often outperforms linked list when used as a queue. Let's look inside ArrayDeque's architecture. ArrayDeque uses circular array, also known as a ring buffer, to store elements. It maintains two indices, head pointer for the front of the deque and tail pointer for the back. When elements are added or removed, these indices move around the circular array. This design provides excellent cache locality because elements are stored contiguously in memory and all operations at the end are O of 1 amortized time. Here is how to use ArrayDeque in practice. ArrayDeque provides a rich set of operations for both ends. You can use it as a stack or a queue or a general purpose deque. Here are common operations. You can create array deque like this. You can add element to front using add first or offer first method. You can add element to the back using add last or offer last method. You can remove from front using remove first or poll first. You can remove from back using remove last or poll last. You can pick without removing using pick first or pick last. You can use deque as a stack, and you can add element using push or remove element using pop. You can use ArrayDeque as queue, add element using offer, and remove element using poll. Now let's move to thread-safe Deque implementations. BlockingDeque extends both the blocking queue and Deque interfaces, creating double-ended queue with blocking operations. This means it supports all the operations of regular Deque, but with added ability for threads to wait for space to become available when adding elements, or wait for elements to become available when removing them. This combination makes BlockingDeque incredibly powerful for concurrent programming patterns. Let's examine primary implementation of BlockingDeque. Linked BlockingDeque. It is a thread-safe, optionally bounded implementation of blocking deque based on linked nodes. Each element is stored in a node that contains references to both next and previous nodes, creating doubly linked list structure. This design allows efficient insertion and removal at both the ends while maintaining thread safety through careful synchronization. Let's understand its threading model. Linked blocking deque uses single reentrant lock to synchronize all operations along with two condition objects, not empty and not full. When thread tries to take an element from an empty deque, it waits on the non-empty condition. When thread tries to put an element into full bounded deque, it waits on not full condition. This single lock design is simpler than two lock approach used by linked blocking queue but can create more contention under high concurrency. Now let's look at iteration patterns. Linked blocking deque provides weakly consistent iterators, which means they won't throw concurrent modification exception but may not reflect all concurrent modifications. For some use cases, you might need stronger consistency guarantees. Here is linked blocking deque in action. Linked blocking deque can be created as bounded or unbounded and supports blocking operations at both ends. This makes it ideal for producer consumer systems where tasks might need to be added with different priorities. So we have blocking operations like put first, put last, which block if deque is full, and take first, take last, which block if deque is empty. There are some non-blocking alternatives like offer first, pull last with timeout mechanism. Let's explore concurrent deque implementations. Concurrent linked deque. While it's not part of the blocking deque hierarchy, concurrent linked deque is an important alternative worth mentioning. It's non-blocking and thread-safe deque implementation based on linked nodes. It uses atomic compare and swap operations instead of locks, which can provide better scalability under high contention. However, it doesn't support blocking operations or capacity bounds, making it suitable for different use cases than linked blocking deque. Here is concurrent linked deque in action. Concurrent linked deque has no capacity limits. It will grow until it exhausts available memory. You can create concurrent linked deque like this. You can add element to both ends using add first, offer first, or add last, offer last. You can remove from both ends using pull first or pull last. You can pick without removing using pick first or pick last. Now let's compare these implementations. ArrayDeque provides maximum performance for single threaded use with O of 1 operations at both ends and excellent memory locality. Linked blocking deque offers thread safety with blocking operations and optional capacity bounds, making it ideal for producer consumer systems. And last, concurrent linked deque provides lock-free thread safety with better scalability under high contention but lacks blocking operations and capacity control. Each serves different needs in the concurrency spectrum. Now let's explore one of the most important patterns enabled by Deque. Work stealing pattern is a scheduling strategy used in modern concurrent systems where idle workers steal work from busy workers. Each worker maintains its own deck of tasks. Normally, worker processes tasks from the front of its own deck, that is last in first out order for cache efficiency. When worker runs out of tasks, it becomes thief and steal tasks from back of another worker's deck, that is first in first out order to minimize contention. This pattern is used extensively in Java's ForkJoinPool and provides excellent load balancing. Let's understand why work stealing is efficient. Work stealing is efficient for several reasons. First, workers normally process their own tasks from the front, which has good cache locality because tasks was recently added. Second, when stealing from another worker's deck, thieves take it from the back, which are older tasks that the owner is less likely to be working on soon. Third, contention is minimized because owners and thieves operate on a opposite end of a deck. This design balances workload efficiently across all available threads. Now let's implement a work stealing system. Here is simplified work stealing system using linked blocking deck. Each worker has its own deck, and when worker's deck is empty, it attempts to steal from other worker's deck. The code creates an array of decks, one for each worker. Think of it like giving each worker their own personal task tray. If we have 4 workers, we create 4 tasks. Then we distribute the tasks among all workers in round robin fashion. Then we create a thread pool, which is just a manager that can start and stop worker threads efficiently. Now let's start each worker thread and see what each worker does. Each worker follows a simple routine in a loop. First, they check their own task tray. If they find a task, they do it. If their task is empty, they look around at other workers' tray and steal from someone who has too much work and execute that task. This keeps all workers busy and makes the whole system efficient. Now, let's discuss interruption handling in blocking deck. Like all blocking collections, linked blocking deck operations can throw interrupted exception. Proper handling is crucial for responsive applications that support cancellation. The standard pattern is to catch interrupted exception, perform necessary cleanups, and restore the thread's interrupted status. Let's discuss critical best practices. First, prefer ArrayDeque over stack or linked list for single threaded deque operations due to its superior performance. Second, use linked blocking deque for thread safe blocking operations with capacity control. Third, consider concurrent linked deque for high concurrency scenarios without blocking needs. And fourth, implement proper interruption handling for all blocking operations. Finally, let's review key takeaways. Deque implementations provide powerful tools for both single-threaded and concurrent programming. ArrayDeque delivers maximum performance for single-threaded scenarios with excellent memory locality. LinkedBlockingDeque offers thread-safe blocking operations with capacity control, ideal for producer consumer systems and work stealing patterns. Concurrent linked deck provides non-blocking thread-safe deck, better for many producers and consumers. By choosing the right deck implementation and applying patterns like work stealing appropriately, you can build efficient, scalable systems that make optimal use of available resources. If you found this video helpful, please give it a thumbs up and subscribe for more technical content.